Good morning, everybody. Welcome to our tutorial on deep learning and information theory and emerging interface. So, as introduced, this is the three of us are going to be presenting, myself, Hyeji, and Sewoong. And much of this is joint work with Pramod Vishwanath, who couldn't be here today. Okay, so as most of us know, deep learning has seen tremendous successes in the last decade. It is so pervasive now. For example, if you see here, the first breakthrough in deep learning was really in speech processing, Siri and Alexa being contemporary examples of daily usage of this technology. You see here an example in image recognition. After ImageNet was cracked, this is an image captioning example where the deep learning system is automatically annotating this image as a construction worker in orange safety vest working on a road, which is very perceptive. In natural language processing, there have been tremendous breakthroughs. This is an example of an unsupervised learning method which learns semantic relationships between words called word-to-vec. And the words are embedded in a dimension, and it automatically picked out, for example, that the direction to go from man to woman is the same direction to go from uncle to aunt. So these are high-level semantic relationships and analogies that the learning system is able to capture. I'll show you one quick example of a video.
I grew up without my father around.
Without retiming, he moves randomly and appears unnatural.
Well, I wonder what my life would have been like.
This is an example of
mother-in-law,
synthesizing.
And so,
so the input to the system is the audio stream, and the output is Obama speaking a video stream of Obama speaking that audio stream, right? So you can see it's very uncanny, the head movements and other things. This is
manufacturing,
clean energy, the CS department,
and the infrastructure that creates good new jobs.
So there are four different,
not to mention the job training that helps folks earn new skills to fill those jobs. The results are clear. America's businesses have created 14.5 million new jobs over 75 straight months.
So, as you can see, some of these breakthroughs are really stunning. And in this tutorial, we will examine some of the basic questions underlying deep learning and how it interfaces with information theory. As you saw, the title was Success of Deep Learning. The success of information theory is well known in our community, so I'm not going to sell ice to Eskimos. So the main question that I start is, why does deep learning work? If you see all these examples, a continuous running trait is that there is severe model deficit. We have no good mathematical models to describe image, speech, language, video data. There is no good mathematical modeling, and maybe this is the reason why we need to use black box methodology like deep neural networks to actually solve this problem. However, this cannot be the only explanation. Why? For example, another major breakthrough in deep learning is AlphaGo, where a computer-trained agent can actually play Go better than a human champion. And AlphaGo is comprised of simple mathematical rules, very precise, having no model deficit. So something else also is underpinning the success of deep learning in some of these examples. We call it algorithm deficit. Even when the mathematical model is fully well-defined, the space of algorithms is so large that it's almost impossible for us to get the optimal algorithm just by thinking about it. So in these contexts, it could be that deep learning can play a major role. So we will see in this tutorial, the view that we take is mainly to understand the algorithm deficit, even in contexts where there is no model deficit, where the models are mathematically very precise, the kind of thing that our community is used to working with. Okay, so coming from a personal story, I got initiated into this deep learning because we were doing some nanopore sequencing, where a DNA goes through a nanopore and you observe some current measurements. And from these current measurements, you have to decode what the DNA bases are. And while doing this problem, we worked with a physicist who gives us very detailed mathematical model. And the model is very similar to a Markov model. So you would assume that you can do optimal inference using standard algorithms like the Viterbi algorithm to actually solve this problem. And that's what our assumption was. We were modifying these algorithms to tune to the particulars of the model. However, we came to a striking realization that even though the process has detailed physics, our models were nearly accurate, deep learning does better. And this is on real data, and this is not just our personal experience. Oxford Nanopore, the giant in nanopore sequencing, shifted from hidden Markov models to deep learning for these problems, even though we understand a lot about the physics of this problem. So again, there is no model deficit, purely algorithm deficit. So we will revisit this particular issue of Viterbi algorithm in a case where there is purely no model deficit, where the data comes from simulations. We'll come back to this as we go on in the tutorial. So this was really our motivating point to actually dive in to understand whether there could be other scenarios in information theory where such methodologies could be useful. Okay, so the title says Information Theory and Deep Learning, an Emerging Interface. And if you think about it, there are two natural interfaces. How can information theory enrich deep learning? This is one direction, and maybe the direction that comes to most of us when we think of this interface. So if you see here, one obvious thing that information theory plays in machine learning, in particular in deep learning, is setting up of training objectives, like cross-entropy loss, scale divergence to minimize. Recently, information bottleneck has been proposed as a new methodology. All these things are information measures setting up training objectives. For example, if you want to control how much bias an algorithm has, you may want to bound the conditional mutual information between certain quantities. So it sets up several training objectives for deep learning. I think the second interface of what information theory can contribute to deep learning is the information lens. So in our community, we're used to asking questions about precisely how many samples do we need to recover the parameters or to recover the information about some underlying process. And this is in deep learning, this would be called sample complexity bounds, but this is really an information theoretic lens underpinning this view. So questions on representability, generalizability, trainability, all these things have some information lens. We can use that to look at it. So the somewhat non-obvious part is, can deep learning help information theory? Information theory is a very model-based, precise, mathematically formulated domain. Is it possible that ideas and breakthroughs in deep learning can have ramifications on information theory? And it can if the information theoretic problems, even though the models are clean, the optimal algorithms are unknown. Take, for example, the insertion-deletion channel. It's a very simple mathematical model, wide open problem for several decades. Can we bring deep learning to actually solve, at least empirically, some of these problems? And when is it likely to work? When the data or the algorithm has a structure like hierarchy and invariance, which is exploited through the general inductive bias that underpins deep learning. We will focus more on these as we go through the tutorial. So that brings us to the organization of the tutorial. So as we saw, there are two interfaces, and our tutorial is organized in two parts. The first part is about how deep learning can be used in information theory. And there are going to be two parts, subparts in it, 1A and 1B. 1A is in particular in communication in codes, code design. And B is, can we use this in information estimation, property testing, so that is statistical inference. In part 2, we are going to ask, can we take the information lens and understand some of the deep learning problems? And we're going to look at generative models, an unsupervised learning example. And we're also going to look at one example on learning neural networks. So this is the organization, and so before we delve into these 4 parts, Sewoong will give an overview of the setup of deep learning.
All right, sorry. So I'm going to give you a very, very short primer on neural network. And my goal is that later, me, Sreeram, and Hyeji are going to talk about the main tutorial. And they're going to throw in terms like backpropagation, autoencoders, RNNs, and neural networks. But as we, as the audience, have different varying depth of background in neural networks. So my only goal here is to set everyone on the same page when we throw in those terminologies. All right, so let's start with the simplest canonical problem, which is classification, which is that we are given labeled examples like xi's, which can be images, together with yi's, which are the labels, could be whether it's a dog or person or different labels. And given this, what we want to do in classification is that we want to find the function that maps the example image to the label such that it minimizes the average loss defined in this way for some particular choice of our choice of a loss. And again, during the whole tutorial, if you have any questions, please raise your hand and stop us. And can you hear me okay back there? Is that a question? You're okay. And can you see it okay? Kind of? There's nothing I can do about the slide, the height of the screen. All right, so that's what you would do if you have infinite samples or know the distribution. You would optimize this, minimize this loss over the whole class of the functions. But as we don't have the distribution itself, we only see it through the samples. What we do in practice is instead we minimize the empirical loss average over the samples that we have. But if we solve this over the whole function class, what's going to happen is that you'll be perfect in all of the training examples that you have, but on all the rest, you'll be completely giving a garbage because you'll be overfitting to the training examples. So the canonical way of solving it is to optimize over another function class, let's say calligraphic f, which is smaller, so that it avoids overfitting. There's a question? Can I repeat what I said? Is a question? Oh, okay, that's a good question. That's the beauty of neural network, is that there are many choices of choosing the calligraphic f function class. This is a primer. I'm not going to go into any details. I'm not going to show you any pretty pictures. I'm just setting the notation for the later parts. And one thing I want to say is that the beauty of neural network through the decades of empirical successes, what it's telling us is that it has a very graceful trade-off between generalization, avoiding overfitting, and representation, actually representing the complex function that we started out with to find. And that's, in like one sentence, the success story of neural networks. Again, thank you for asking questions. Everyone, please stop me or anyone if you have any questions. So what is a neural network? It's a parametric family, let's say, parameterized by a layer of computations of depth, let's say D, and each layer is parameterized by a matrix, W, of dimensions. So it's represented by a computational graph like this one. So on the left-hand side is the input data x of a fixed dimensional vector, and each node or the circle represents a scalar value of the vector entry. And what its layer represents is that, let's say if you're computing something in the first hidden layer, then what it's going to do is it's going to take the weighted sum of the inputs, all these are scalars now, weighted according to the weight that we're going to optimize over, that's the parameters, and in the end take a scalar to scalar function of nonlinearity, typical choices being either sigmoid, ReLU, or tan-H, and there are many different choices. And this operation is recursively applied to compute the last layer, which will be the function of the x that we want to use as a prediction. And the whole thing can be represented as a vector matrix multiplication and entry-wise nonlinearity. Okay, and if you have a trained function, that's how you compute the output. But when you're training, you first make a choice of a loss, and we're using binary classification as an example. And what you're gonna do is, you might minimize the L2 loss between the label yi, this is either 0 or 1, and our function output f of xi. That's one example. Another common example people use is cross entropy or KL divergence loss, where you minimize this particular loss. And here, what you're asking f, the function, to do is predict or estimate the probability that y label is equal to 1 given x is equal to the example that you have in your hand. And what you're minimizing is the cross entropy or KL divergence between the true distribution and then your output from the function f. And many variants of gradient descents, like stochastic gradient descents with variance reduction, are used to compute the solution of this optimization. And one important part of neural network is that the gradient of the function of this form can be computed efficiently because it's a composition of many simple functions, and using chain rule, which is called backpropagation, the gradients are efficiently computed and gradient descents are used. Right. Another part of neural network that I did tell you is that feed-forward neural network, what I just explained, works fine if you have a fixed size vector inputs. But in scenarios like translation, you have inputs that are sequential and of varying length, meaning there's a natural notion of direction of time, and the length of the input vector might change. And to account for it, recurrent neural network has been proposed. And what it does is it captures the causal structure through memory. So recurrent neural networks are neural networks that have a sequential structure. So every cell at a certain point in time will be some single layer neural network takes as input the example at that time, let's say, perhaps a vector representation of a word, together with the hidden memory cell of the previous time step, computes the next time step's memory cell, and each cell can output in some dimension vector as a function, again, simple function of the memory. In this example, this is an example where you have a rating of a restaurant, and you want to identify whether it's positive or negative. And how you would do it, you turn each of the word of the sentence into some vector representation, run it through recurrent neural network, and try to output a real number representing how positive the review is. And another part of machine learning is called unsupervised learning, where you're given, in this case, only the examples xi's with no labels, and you want to learn some useful representation f of xi, which is a vector, possibly of lower dimensions. And what is useful depends on what application and who you talk to, but typically what you want a unsupervised representation to do is give you some dimensionality reduction in the sense that you can reduce it 2 or 3 dimensions so that you can visualize it. Or maybe you can use it for efficient processing, like Johnson-Linden-Strauss sense, maybe to compute nearest neighbors and other things. And another way to use it is like rate distortion or compression. You want to compress a given file, perhaps, or image. And the last one is the representation itself can be used in some downstream tasks to solve other problems, as in word-to-vec has been very popular in natural language processing. And one way to do it through neural network is called autoencoder. And the premise is more related to compression, where you're saying a good representation should be able to recover the original data. And that naturally leads to a autoencoder architecture, which is you have the encoder, which maps, this is a feed-forward neural network, maps the input x to some lower dimensional learned representation, which is again passed through a decoder, which maps it back to the dimension of the original space. And the hope is that the estimated original data, x, going through this bottleneck of dimensionality reduction, is close to the original one. And typical losses is L2 loss on the original data and the recovery, and you minimize it over the weights of this whole neural network. And this has been very successful, not in just compression, in many of the tasks. Again, my goal in this primer is just to set the notations for everyone here. And the details of these will be coming up as we go through the tutorial. And perhaps the last one in this primer is going to be another part of unsupervised learning called neural network generative models. One way to learn a generative model which can model a probability distribution by being able to produce the samples is called neural network generators. And it's simple. It'll be some feed for neural network. But at the input, what you do is you create a lower dimensional vector which comes from some simple distribution like IID Gaussian. And the neural network learns to map it to a space of dimension that we want. For example, in this case, it's a 1,000 by 1,000 dimensional image. And the weights can be trained in some way so that it can replicate the realistic samples, like this one will be an image generated by a learned generator. And how we do it is called generative adversarial networks, and big chunk of our tutorial will be on it later. And that's the end of my primer. And with that, we're going to start with the main part of this tutorial. So Hyeji is going to tell us about part 1A, which is applying deep learning to solve important problems in communications and code design.
Okay, so I'll talk about the application of deep learning to communications. So from the whole tutorial, this part stands in the 1A, part of the deep learning application to information theory. Okay, so in communications, oftentimes the models are quite well defined. Here I'm showing a very fundamental basic communication system where there is a transmitter which maps a message to a code word called encoding, and then a receiver which takes the received noisy code word and decodes it and recover the message. So for reliable communications, it's very important to have a good pair of encoder and decoder. But the challenge in designing this code is that the space of algorithms is very large. For instance, if you have 100 message bits, you have 2 to the 100 different messages. And you somehow have to map all of them to a code word and then demap from the noisy code word back to the original messages. So it's an algorithmically challenging problem. And it's very important for reliable communication and has been one of the central problems in information theory society and also in communication society. The progress, however, has been quite sporadic. Since around 1950s, there has been a huge effort. A lot of human ingenuity has gone through it to discover new codes. But new codes were discovered like around once every decade. And most of the work in the code design has been focused on the canonical channel, which is additive white Gaussian noise channel, where the receiver observes the code word plus the Gaussian noise. And under this channel, after like 7 years of research, we now have good codes that work pretty close to the fundamental limits, like turbo codes, LDPC codes, and polar codes. On the other hand, however, there are many open problems. And broadly, there are two types. The first type is where we do not have a good code at all. We don't know good encoder or decoder. We don't know both of them. Okay? And the canonical example for that is network settings. In a lot of simple network settings, even now, we don't know, we don't have good code, and we actually don't even know what the fundamental limits are. So it's widely open. Another setting is channels with feedback. The communication can involve feedback from the receiver to transmitter, and the feedback can be in various forms. And how to make use of it is still yet not so clear. And I'll talk more about this part later. And another example, as Sreeram mentioned in the beginning, is deletion or insertion channels, simple point-to-point channel, for which we don't have good codes, we don't know capacity. Okay, so that's the first type. The second type of open problems is where we do not have good decoder. So in practical communication systems, oftentimes the encoder is fixed. It has to follow the communication standards. And these encoders typically come with a very good decoder under AWGN channels. But the practical channels are not always AWGN. And how to design a decoder that is adaptive and robust to non-AWGN channels is an open problem. Indeed, more broadly, designing a reliable decoder for some complicated channel, some complicated practical channels, is widely open. Okay, so these are two types of open problems. And the question is, in solving these problems, can we bring deep learning to search for codes and decoders and automate the process? And in this tutorial, or in my part, which will be in two parts, the first part is on discovering new codes, and the second part is on discovering new decoders. I'll show some successful examples where we do this. And then I'll talk about some other works in the literature, and then I'll conclude with very interesting open problems in each part. So let me get started with the first part. Okay, so the problem we looked at is channels with feedback and learning a code for it. So modern wireless communication involves feedback from the receiver to the transmitter in some form. And the feedback can be some various things. It can be the received value itself, or it can be some quantization of it, or it can be a repeat request. And there can be delay in the feedback, or the noise in the feedback. So there are various channels. And we're going to look at the canonical channel for this that captures the essence of the feedback channel, which is proposed by Shannon and also studied by Shannon. That is AWGN channel with output feedback. So from the transmitter to receiver, we assume AWGN channel. And the receiver just transmits back what it has received. Then there's a noise, Gaussian noise added to it, and the transmitter will receive the feedback in one time step later. Then the transmitter can use that information to determine what to transmit next. Is the setting clear? Okay. So that's a problem. And as a special case, if there is no noise at all in the feedback, then there are very beautiful results. So it is shown that the reliability can be greatly improved. We can achieve doubly exponential block error rate as block length increases. And also, there are well-known coding schemes that theoretically achieve this improved reliability, such as Sharkov-Kyla for AWGN channels with feedback and posterior matching in general. So that's a nice story. But what if there is a noise added to the feedback? The story becomes totally different. The existing scheme is highly sensitive to noise. It doesn't really work well. Indeed, there are negative results saying that any linear code that makes use of the noisy output feedback cannot achieve a positive rate of communication. It's on highly negative results, and it's widely open. So we focus on this channel. Okay. So if you think about this problem, the reason why it's very hard to design code is it's not clear how the encoder should make use of the noisy output feedback, but at the same time transmit the message. So in our approach, we model the encoder and decoder both as a neural network, and then we'll train them together. Okay, before I talk about the details of our approach, let me first show you the results. So we are looking at a setting where the feedback is noiseless, but precise up to the machine precision of 16 bits. And this black curve is Sharkov-Kyla, and the red one is neural scheme that we train. And this blue dotted curve is turbo, which does not use any feedback. So, and this BR is in log scale. So in fact, neural code is actually like around 1,000 times better than Sharkov-Kylog, which is a big improvement. And also, we tested the robustness to the noise in the feedback. So we are going to fix the forward SNR, and then now we'll vary the feedback channel SNR, and then plot the BR as a function of feedback SNR. And again, this red one is neural code, and the black one is Sharkov-Kylog, and the green one is another code proposed by Chance and Love, designed for noisy feedback. And we can notice that neural code is again much better in terms of reliability, and the bit error rate decays as feedback SNR increases. So it is making some use of the noisy feedback. Okay, so that's the results. And now I want to show how we got this performance. In fact, if you simply apply any like deep learning, it will not give you a good code. And we have to bring a lot of architectural innovations, and also critically, we have to bring ideas from communications and information theory. So we had to go through some steps to get the final performance. I'm going to show you the steps that we went through, okay? Okay. Let me first show you the baseline scheme for our code, the very first step. So I'm going to show you how the encoder works. The encoder works in two phases. So here's an example. Let's say we have message bits B1, B2, 3, and we are given 6 time slots to transmit something. Then in phase 1, we will simply throw the bits. We'll just send it, say using PPSK. And then we get the feedback on what the receiver has received, Y1, Y2, and Y3. And now, given this feedback information, in phase 2, we can use this feedback to generate parity bits to further refine the transmission. And there are many ways to do it, and this is what we propose. We will start with generating a parity for the first bit, B1. And there, we are going to consider what the receiver has received. So the parity 1 is some function of B1 and Y1. The thing is, we don't know what this function should be. That's what we want to learn. But anyway, we will just have some function of P1 and Y1, okay? Okay, and then we'll transmit it, right? So we transmit C1, and then what happens? We get feedback, YC1. At this point, since we are given YC1, we can further refine the information on B1, considering YC1 as well. But then what about B2? So alternatively, we can just ignore YC1 and generate another parity, which is refining information on B2. But ideally, we want to do all of them. We want some parity that's both telling about P2 as well as P1. That will be the best, right? And then we transmit YC1 against some black box. We transmit C2. We transmit it, get feedback YC2, and then in next time step, we're going to refine information about B1, B2, and B3, considering all the feedback that we have. Right. So these are all black boxes. But the thing is, okay, and then we're going to model this black box as neural network, and we want to figure it out. But one issue is that towards the end, there are more and more things added as an input, right? So we want a neural architecture that has memory in it. And recurrent neural network is a good model for sequential mapping with memory. I'll just briefly go over it again. So there is a hidden state evolving through time. And the hidden state captures something about the input. And the hidden state is updated as some function of the previous hidden state and the input. The output then is another function of the hidden state. And we will model the f and g as some parametric functions. And depending on what parametric functions you choose, this recurrent neural network can be vanilla RNN or GRU or LSTM. All right, so we model it as a parametric function. So it's an encoder architecture. Now, we need a decoder as well. And given that the encoding process is sequential, it's natural to use sequential architecture for a decoder as well. And bidirectional RNN, now we don't have the causal constraint. We can just wait to get everything. So the receiver will take all the output receive values and then couple the receive values from phase 1 along with the receive value from phase 2 and then do the RNN decoding and recover the bits. So now we have encoder architecture, neural network, parametric function, decoder, also parametric function. Now the last thing is to learn good parameters. And how we do it? We learn them jointly. We'll model the whole communication system as one large neural network. The input to the neural network is message bits, and they will go through encoder and decoder, and the output of the neural network is an estimated message. So it's like an autoencoder. And the goal of training then is to find the parameters that will give B hat as close as possible to B, right? Okay, so when we generate the training examples, we generate the random message bits sequence, B1 up to say BK. And then for loss function, we are gonna use binary cross entropy because it's a classification problem. And the length K is what we can choose, the length of the training examples. And it turns out it's quite important to have a pretty good K. And we find that even if you want to find a good code for a short block length, still it's good to train with a large block length example to learn a good structure in it. All right, so we learned it, and we got the PR curve. And the green one is our curve. That's very impressive. It's not really good, right? I mean, it's sometimes better, but not satisfying. So we did a typical error analysis. Why is error happening? So what it's going to do is it has receive value from phase 1, right? And receive values from phase 2. And these are all, in some sense, the most informative about, these are most informative about B1. These are most informative about B2. And these about B3. So this is how we model the decoders. Okay. All right. Exactly. That is why, thanks for the question, that is why there's a connection in it. So this RNN has a memory. So we'll keep some information about this input and then pass it through here and here. Okay. Nice. Okay. Great. Okay. So that's a good question. And we train with the matched SNR, and that works the best. Even if you do a mismatched training SNR, you train some SNR test and other SNR, it works pretty well. But the best result can be obtained when we train with the exact same SNR as a testing SNR. Great. Okay. All right. Okay. So, right. So we did typical error analysis. When does error happen? And we plot the BR across position. And then we figure out that not symmetric. The bit in the beginning has smaller error. The bit in the end has large error. Why is this happening? In fact, from the neural encoder architecture, it's not too surprising because all these parities carry information about P1, right? But only the last parity carries information on P3. So this naturally gets somewhat penalized. It gets less information transmitted. And to resolve this issue, we bring a simple idea from communication. Any guess? So, exactly, that's what we tried. So we pad a 0 in the end, and we generate the corresponding parity for that. And that turns out to give a huge improvement in BR. And still, there are more errors in the end than smaller in the beginning. Any other things we can try? We tried power control. If we use more power for the last bits and smaller power in the beginning, we can somehow balance it out and get nice even performance. But we don't know how much power to put where. So we introduced a trainable weight and then train it. Turns out neural network figures out it should use more power in the end, smaller power in the beginning. And now it's more of flat. But what's impressive is the overall BER has dropped significantly by 10 times. OK, so this is how we got to the final performance. And this is the bit error rate as an SNR with the machine precision. And also, I'm here showing the block error rate as a function of SNR, not only compared with Turbo, but with other best state-of-the-art for error correcting codes, such as Turbo or LDPC codes, convolutional codes. And this is Sharkov-Kalla. And another comparison points are normal approximation and converse, for which we do not have practical codes at all. So we are making a strong use of feedback, and then we are getting good performance, even in block error rate wise. All right, and then in robust noise in the feedback. And now I want to mention from more practical perspectives, noise in the feedback is clearly one practical constraint. But another constraint is there's delay in the feedback, right? So we considered, and we shown that to take the delay into account, we can modify our encoder a little bit, and then get this BER performance. Not as good as instant feedback, but still it's better than the other two baselines, and the error rate goes down. So we are making some use of delay feedback. And then another interesting we've done is in the feedback, if there is noise, natural thing to do is to code. So now we allow the receiver to code its feedback, and that will actually give like 3-4 times improvement. And that's the new curve. That is true. Yes. So the question is, can decoder do decoding on the fly? No, it has to wait to receive every bit and then decode it. So, right. So in this curve I showed, we are considering length 50, and later I will show generalization to longer block length. 50, yeah, 50 bits. Yes. Thanks. Mm-hmm. Yeah. So here, when I talk about the delayed feedback, that means you can wait to get like the receiver can wait till getting K received symbol and then transmit it. Transmit back. Oh, multiple copies. Yeah, we can talk offline. Yeah. Okay. All right. So far I talked about how we can bring information theoretic ideas and communications to design a good code. Now I want to talk about going the other direction. Now, given that we have powerful code, how can we interpret the code and get any meaning out of the learned code? Exactly, yes. And we train them jointly. Yes. Great. Okay. So now I want to understand, I want to look at like, what is this code really doing? We want to make some meaning out of it, right? So we look at the code. So to understand the code, we want to understand how these parities are generated as a function of all those past and current inputs. Right. Okay. And one note here is I explained the code in the rate 1/2, but we are actually looking at rate 1/3 code, meaning this parity is a couple of parities. So we have actually 2 parities. Okay. All right, so we have 2 parities per each cell, and now we want to look at how it depends on the inputs. And in particular, the first thing to try is how does parity depend on the information bits? That's true. So we plot the parity as a function of pk, so this is ck1 and ck2, and then we see some pattern. You can see like there are some skew here. There's more negative, more positive, more negative, more positive. But the variance is too high. Doesn't really explain. So it means that we are making use of feedback, right? So we plot the parity as a function of the feedback, like yk. And we actually plot as a function of yk minus pk, same information, but this is just simply a noise added in the case of transmission in phase 1. Some complicated form, right? But what we noticed is that sometimes the CKs are quite small, sometimes it's large. And what makes this separation? So we look at the cases where CKs are small, when it's pretty small. And then we realize that if pk is positive and the noise is also positive, then ck is small. Or if pk is -1 and noise is negative, then the ck is also small. Meaning we don't really need to further refine. The receiver already has a correct information, very likely. On the other hand, if pk is minus and the noise is positive, then potentially the receiver has wrong information, so we further refine it by transmitting the noise. This is actually proportional to the noise here, so we resend the noise so the receiver can cancel the noise out. Does it make some sense? Okay. Yeah, so this is like a first-order interpretation of the code. But these parities also depend on the other past bits and the noise as well. For example, if you look at the correlation coefficients between the parities and the previous information bits, there are some associations. The memory seems to be around like 2 to 3. But having a precise, understandable mapping from all the past and current bits and feedback to the parity is yet mysterious. What we know, though, is it seems to be quite complicated thing. We looked at, it seems like the neural code actually require around 50 hidden states evolving through time that is capturing some complicated functions. That is what we understand. But as an open problem, proposing an interpretable encoder that we understand precisely, that works well, maybe not as good as a neural code, but still pretty well, is an interesting open problem. For the decoder side, we can either train a neural network to decode the code, or we can analyze the error performance theoretically. That will be even nicer. Right. And we look at the generalization to longer block lengths, as I mentioned. And what we noticed is that the BR remains about the same. This is probably because the memory in the code is not too long. It doesn't really have a long-term memory, seems like. So we don't really gain in error rate as we increase the block length, and this is not very nice. For example, turbo codes or any forward error correcting code has very nice property. Block error rate decays as block length increases. So we also want to get this performance, right? So we tried concatenation idea, which is we keep the feedback code, but we first we concatenate the code with the traditional code like turbo code. So for instance, I'm here showing concatenation of turbo code rate 1/3 with feedback code rate 1/3 is the red one, and the blue curve is the turbo rate 1/9. And then we also have a nice error decaying property, and it decays faster than the code that does not use any feedback. So that's a nice property. But on the other hand, this concatenation comes with a cost of rate. So although we are given rate 1/9, we are only using coding gain of rate 1/3, and we are only using feedback gain of 1/3. and this is not very nice. So we ideally want to have a neural code that has a long-term memory and also make use of feedback. But that's a pretty hard open problem. We can try to have an interleaver in the feedback code, so we can have an encoder that looks somewhat like turbo code. But the problem is in decoding. We don't really know how to decode it. Because the thing is, we need a belief propagation decoder, which takes the component decoders, which maps the noisy code word and prior likelihood to posterior likelihood. So we want this component decoder, but we cannot really train them yet because we don't have labels. We don't have true labels, so we can't train. So that's an interesting open problem, also the interesting neural network problem. So anyone interested, please take a look. Okay, so that's an open problem. Any questions here? All right. So that was the first part on the one successful example, gaining the improvement. Yes. Okay.
So the neural network adapts according to the channel condition, right?
So
If the channel SNR changes, the neural network is going to change.
yes, that is right. If you do not change, if you use one neural network and test it on various SNR, it will be still better than the other baseline, or it will be pretty good. But the best performance will happen when you use the matched model for the SNR.
So does that require synchronization between the transmitter and the receiver? That the receiver needs to know what the parameters are in the neural network? Or they can do it blindly. The receiver doesn't need to know how the transmitter encodes the bits. It can learn it from the receiver.
I see. Yeah, so the receiver doesn't need any side information. It just needs receive values, and then it's good enough to decode.
So it knows how these bits are generated based on the just based on the receiver.
Okay, so what the receiver will do is it will not, actually, yes. So receiver can, okay, so if there is, okay, two scenarios. If the receiver knows the SNR precisely, then it can use the matched decoder for it. Alternatively, if the receiver does not know the SNR, it will use one model, and it will be not as good as the best one, but still it will be pretty good.
If you want to adjust the neural network, then the receiver has to know.
Yes. But it degrades gracefully, so it's okay. Yeah. SNR as a feature. I see. No, we haven't tried that. Maybe that's another, yeah, that's a generalization idea. Okay. Alrighty, so I'll talk about some other works in literature. And there are three broad themes. The first theme is to learn a good code for 8WGN channels. And what is known is that by training a neural network, you can get a 7-4 code, which means 4 message bits and length 7 code word. And that neural code works as good as a 7-4 Hamming code. One of the very beginning works in this area. And another work is that it is shown that by mapping 128 information bits to 128 complex symbols, you can get an autoencoder that is 5 dB better than the QPSK mappings. So these are some interesting results towards the 8WGN setting. And another line of work is on when there is model deficit. Model is not clear. So some authors propose an idea for training under channels without a stochastic model. And the proposition is that you first train the encoder and decoder jointly under some stochastic model for it. And then in the second phase, you train only the decoder with the real channel. And the other authors further propose how you can further train encoder and then decoder and encoder and decoder. There are some lines of work to deal with the channels without clean model. And The last line of work is where the channel is clear, but the source is complicated, like text. And the authors show that by jointly doing the source channel coding, we can get an improved reliability, where the reliability is evaluated by human. And there are also many other interesting works, very nice works. Things like on coded computation, and OFDM, and MIMO, and many other communication problems. And about the open problems, the first open problem is not really to discover the codes that beat the state of the art, but at least we can start with saying, can we learn the good codes for AWGN? The bar is high. I mean, 7 decades of research has been gone through it. So can we learn the codes for AWGN? And it's quite hard, and two challenges. One is, like I said, getting a neural code that has long-range memory is very challenging. And also, we tried hard in this problem also, but the issue is when we train the encoder and decoder jointly, there are so many local optima, so we cannot really get to global optima. And after months of research, we now have learned good codes that is as good as convolutional codes under block length, say 100, but it took a lot of effort. So it's a challenging problem, but worth trying. But also, if you beat the state-of-the-art codes under AWGN, they will have a huge practical impact. It'll be a nice result. And then perhaps more interestingly, finding a new code for channels without good codes is very interesting, like in dilation channel, which are practical and optimal codes are known only if the dilation probability is very small, very special cases. And lastly, many network settings are widely open, and discovering codes for network settings like relay channel, interference channel are all very interesting. Okay, so now I'll talk about the second part, which is discovering decoders. Okay. Yeah. Uh-huh. Mm-hmm. That's an excellent question. Yeah, we have some results, but exploring a whole possibilities is an open problem, very interesting open problem, and practically important as well. Yes. Oh, the algorithm, the encoder architecture generalizes to any rate of lower rate, I would say, lower than 1/2, and going to higher rate is yet quite open. Yes. All right. Okay, so now we'll look at the decoding part. We're going to fix an encoder and try to learn the decoder. So when we fix encoder, there are many options. We consider sequential codes, such as convolutional codes, turbo codes, and many reasons to it. First is practical, obviously, and also performance is close to the fundamental limits. And also, one important reason is it has a natural recurrent neural network architecture that aligns well with the RNN. So we focus on sequential codes. And what we know is for sequential codes, such as convolutional codes, under AWGN channel, we have optimal decoders already. So we have benchmarks already. So, okay, like Viterbi decoder or PCGR decoders. But the practical channel is not always AWGN, and beyond AWGN channel, decoding becomes more challenging. One example for the non-AWGN channel is bursty noisy channel. Occasionally, a very high power noise is added to the receive value. So in practice, heuristic decoders are used. If the receive value is too high or too small, you threshold it to some value, and then do the decoding. For neural networks, what we do is we simply train a neural network to decode under bursty channels. So the general framework is the following. We fix the encoder, some sequential code, and we choose channel, whichever we want, And then we train the decoder. So we model the decoder as recurrent network because encoding is sequential again. And we do the supervised training by showing the pairs of noisy code word and the true message bit. We learn the decoder so that P hat becomes as close as possible to B. That is the idea. And we are going to start with the very simple case. Before we even get to bursty channel, why not start from a diligent channel? And why not start from convolutional code, which is the simplest sequential code? And then, OK, so we just supervised training. And for loss function, we use mean square error loss. Might not look so natural, but it's another loss function. And empirically worked a little better than binary cross entropy. So we use mean square error. We train it. And then in training, there are two important factors that we have to choose. One is the length of message bit, how large the message bit is going to be. And another is the training SNR, like how noisy would this noisy code word should be like. Okay? And surprisingly, turns out these two parameters are extremely important to learn the decoder. Let me show you what worked. So we trained a block length 100, and we fixed the training SNR to be 0 dB. And then we test the performance across different block lengths and different SNR. OK, now I'm going to show you the result. So this is BR of neural decoder and the optimal decoders under block length 10,000. And we can see that the curves are indistinguishable, right? And also, at block length 100, the curves are indistinguishable. But the natural question related to the question of whether the training SNR should be equal to test SNR. The natural thing seems to be that shouldn't we train at 6 dB if we are going to test at 6 dB, right? Seems natural. So we tried, and this is what we got. If we train at the test SNR, at low SNR, you're OK. But the high SNR, you lose performance. And why is this happening? If you think about it, if you show the high SNR example, you are not really showing the code word, noisy code word, that are near the decoding boundary, right? So somehow you should show the examples that are near the decoding boundary, which means quite noisy examples. And to turn this observation into a better intuition, we did one experiment. Oh, you mean the comparison PCJR?
Yeah, you have not.
Yeah. You assume that it knows it. Yeah. Yeah. We assume that PCJR knows the SNR. Yeah. Yeah. So we are using a two-layered GRU. Yeah, 2 layers is fine. In the end of the output, we use sigmoid activation. And there is no encoder at this point because we fixed the encoder. And only the decoder is neural network. Yes. All right, so we did one experiment to turn this observation into better intuition. And the experiment is the following. We are going to look at different weights of convolutional codes, and then we will empirically find the best training SNR. And then this region is where the best training SNR stands around. And we can see that as the code rate gets smaller, the best training SNR gets lower. What does this mean is as the code rate gets smaller, the code words are further away from each other. So we should show noisier examples. Agree? Oh, So the thing is, in this decoder training, there is not much of overfitting because every example you see is new. Does it make sense? Yeah. So there's no, yeah, okay. So in other words, our training error and test errors are pretty much always about the same. Yeah. Okay, so this is what we've seen. And then here, we plot a curve of Shannon limit, which means at this code rate, if SNR is below this curve, so if the SNR line is here, then it's never possible to decode it reliably. So what these two curves are showing is that we should really train with the examples that are hardest but somewhat doable. And so this is an intuition that we get from this experiment or this research. So the idea is that we should train with hardest but somewhat doable examples. And this aligns well with what's known in neural network, that it's good to train with some noisy labels, noisy examples. And then also this idea can be applied to problems where we can choose a training example. All right, and then, okay. So far, I talked about decoding convolutional codes, and now we're going to look at the turbo codes. So turbo decoder, or decoding of turbo codes, has belief propagation decoder of the PCJR components, which will map the noisy code word and prior likelihood to the posterior likelihood. So to learn decoding of turbo codes, we take two steps. First step is we train a neural network to learn the component decoder, meaning we want to learn the PCJR decoder. And here we train with the actual PCJR labels. And then we stack these component decoders and then train the whole decoder all together, end to end. Okay, so here I said we train the PCJR with the true PCJR labels, and naturally the question is, can we do it without the true labels? And it's very hard. We tried, it hasn't worked yet. It's an open problem, very interesting open problem. Okay, so that's how we train the decoder for turbo code. And then we'll compare the performance. So I'm showing bit error rate for neural decoders and turbo codes under block length 1,000, and they are about the same, comparable. So that's good, that's what we wanted. But then another motivation for this work was what if we look at some non-AWGN channel, like persist channels? But given that now we have good decoders that work pretty same on their AWGN channel, before we do any further steps, we simply tested these two decoders under the persist channels. Like, what if suddenly channel changes? So it's related to robustness. So we take these two decoders, and then we test it under the persist setting. And then surprisingly, we realized a neural decoder is much more robust to the non-AWGN Gaussian noises. Perhaps this is because in this turbo decoder, every formula is exactly suited for the AWGN settings, highly tailored to it. But in neural decoder, we never had any formula, nothing. We just trained them. So it's somehow more robust. Yeah, that's empirically what we see. And then last step is, suppose a decoder knows the channel is going to be burst channel, then we can actually train a decoder or use a decoder that is trained with those bursty examples, or we can use the decoder that is tailored for burst examples. So we train the neural network further with the burst noise examples. So now this is neural decoder trained with AWGN. This is neural decoder trained further with burst examples. And we can see the improvement in bit error rate. And this black curve is the heuristic decoder that's widely used in practice. You threshold large values and then do a turbo decoder. And then if you look at these two, not one is always better than the other, but in some region we are better. The neural one is better than the turbo with thresholding.
So your noisy burst
Uh-huh. Mm-hmm. Right. We haven't done that calculation, went through that calculation, but I would say, but another important thing is if we do that, it will still be tailored to that exact bursty router. But on the other hand, the neural decoder is not too sensitive to how bursty or how large the bursty is, so still neural decoder has some advantage over it. But good point, yeah. All right, so, okay, now I'll talk about other works on discovering decoders. Okay, so the first one is on decoding linear code, such as BCH codes, LDPC codes. And the authors show that we can generalize the BP decoder. So what they do is they take a neural network and they let the neural network to exactly represent the BP decoder. So the initial point is exactly BP. And then there they introduce trainable weights to it, and then train the weight through with the examples. And then they show that that decoder, which is generalization of BP, performs better than BP. So it's nice in the sense that it's an efficient decoder, and it fills in the gap between the BP decoder and the MAC, for example, for PCH code. So we'll increase the error without introducing much more computation. And then another work is on decoding polar codes, also one of the very earliest works. And here the authors learn to decode polar codes from the scratch without any information. Just live feed-forward decoder and then train it. And also decoding under some complicated channels that does not have a clean model has been considered. These authors show that they can decode better than, say, the perturbative decoders under some cases for molecular communication channels. Right, so the open problems on the decoding part is obviously some practical channels with interactable model is a very practically important open problem. And also some other channels like channels in memory or deletion channels are where it'll be great to have neural decoder on. And another perspective is about the adaptivity and robustness and how to have a neural decoder that can quickly adapt to varying channels is also a very important open problem. And to summarize, human ingenuity has been the driving force behind designing code for the past century. But there has been limitations, and we provide an alternative approach of training the neural networks and demonstrate its powerfulness with some feedback code examples. And it has great potential to provide new solutions to other numerous open problems in the society, communications. And the summary really is that it's not just deep learning. You have to bring the domain knowledge and ideas from communications, information theory to get a good performance. And once we do that, we can also get new ideas and intuition to deep learning methodology itself. And lastly, by doing so, we also gain new insights and ideas in the code design and information theory as well. Okay, so with that, I will, and then important thing is I'd like to thank my collaborators. And that is all. Any questions? Okay.
For the feedback code, they have an interpretation of what the neural network is doing. Do you have a similar interpretation for the interpreted CJR or the other decoders you design? What the neural network decoder is?
So good question, because we learned the neural decoder that works as good as like perturbative decoder under AWGN, but it's more robust under non-AWGN channels. So it means neural decoder is different from Viterbi, but but it seems to be Okay, so for example, in the turbo decoder, if you look at the component decoder, like when we train with the PCJR decoder, it seems to be somewhat more, how should I say, like, okay. So in PCJR, sorry, So in PCJR, there is a belief propagation. We take the prior likelihood and give a posterior likelihood. And one thing we know is in neural decoder, the posterior likelihood values are smaller than the actual PCJR decoder. So it seems to be somewhat more like, more robust. Yeah.
So maybe I can.
Yeah.
So when we train the neural network decoder, if you want robustness against bursty noise, especially during turbo decoding, the main thing seems to be that if you estimate the log likelihood ratio very high,
right.
There's a burst interference and then you estimate that LLR to be very high, then the belief propagation spreads that error away. Whereas what happens in the neural decoder is that you never estimate beyond the standard range of -3 sigma, -4 sigma to +4 sigma. Your LLR is in the typical range rather than in the atypical range if you use a PCJR decoder. So it has automatic inbuilt saturation because that is the typical signals that it has ever seen. So this is one interpretability, but a deeper understanding of exactly what the algorithm is doing.
It's open, yeah. Yes.
You use the RNN framework. So this is because of the relation between the RNN and the sequential code. So for the non-sequential code, like the other code, what kind of neural network structure do you use, like SIM or
So the question is, what if the code is not sequential? But for example, for linear code, feed-forward neural network is widely used. And for so for decoding of linear code, the feed-forward network is the traditional thing that people use. And in the autoencoder training, you can use anything you want. And some people use CNN, some people use feed-forward, and we actually tried RNN still. So the training doesn't take too long. It takes in the order of like hours. So it's, yeah.
And then I guess also once it's learned, the decoding should be very quick.
Yeah.
Like, is it even quicker than like the thing you're trying to imitate? Like, can you learn something faster than turbo decoder?
So we implement, cause like, okay.
The cost of decoding is a little bit hard to analyze because it depends on what acceleration you have. For example, you can use GPUs and such to run accelerated inference. And also there have been a lot of work trying to accelerate computer vision, design neural networks with low bit precision. So we can apply some of these ideas here. And just to compare between computer vision and RNNs, the depth that we have is much lower. We have like depth 2
layers
compared to 1,000 layers when I run in a computer vision setup. So we do expect that with appropriate acceleration, which will be faster, but it's open.
Maybe naive is slower than a turbo code.
I think naively it will be slower. If you run on a CPU, it will be slower than a turbo.
Yeah, if in CPU, yes. Yeah. Yes, definitely. Yeah, that's actually one of the very first things we can try to get a long-range memory and extend to high block length.
GRU versus LSTM.
So yeah, they're about the same. Yeah.
We tried both.
Yeah,
and they
similar.
get the same performance for our applications. So we go with the simpler one.
So in part 1b, we will see how deep learning can benefit information theoretic problems, for example, in statistical inference. So this part is joint work with Rajat Sen, who's a student at UT Austin, Karthikeyan, who's a researcher at IBM, Arman and Himanshu, who are at UW Seattle. I've been very lucky to work with all of them, and these slides were designed jointly with Himanshu. Himanshu is also on the academic market, so any of you interested can talk to him. Okay, so we've seen how information theory can be useful in coding, or deep learning can be useful in coding. And in this section, we will see how we can address other statistical inference type problems. And to do this, we're going to use two primitives, which have made a big impact in deep learning: strong classifiers as well as powerful generative models. And we are going to see how to take these building blocks and apply them to problems, for example, in statistical inference, like independence testing, conditional independence testing, information measure estimation, and other works existing on compressed sensing community detection. So let me summarize what we know about classifiers. So deep neural networks and boosted random forests achieve state-of-the-art performance on many real data sets. And what is really surprising, looking at it from an information theoretic viewpoint, is the data X is in very high dimensions. And still, the algorithms are able to perform well by exploiting some kind of prior knowledge. And this prior knowledge is not stated precisely. It is a very interesting mathematical question to actually formulate it. But at a high level, it is exploiting things like invariance, hierarchy, symmetry, in order to infer from the observed data X to the target label Y. And we saw this example of image captioning, where you go from a very high dimensional X, which is an image, to a very high dimensional Y, which is a sentence. And okay, so just one example. And I just like to point out that theoretical guarantees lag severely behind practice by orders of magnitude. And this is one of the things our community should get involved in. Okay, on the other hand, the supervised learning classifiers have demonstrated tremendous success, especially deep neural nets and boosted random forests. On the generative model side, which is you have unsupervised learning data, you just observe a bunch of images, and you want to learn the probability distribution of the images. And in particular, implicit probability models, which allow you to synthesize new examples from the same class without having an explicit probability distribution, have become very popular. One of the topics is generative adversarial networks, which Sewoong will touch upon in detail later. So you see a bunch of real samples and generate a bunch of new samples which look real. So here is a striking example of a generator trained on real celebrity faces and able to synthesize all these faces, and none of them are in the data set by far. So really striking creativity on display. Okay, so now we have powerful classifiers and generative models in our hand. How can we go and attack some of the basic inference questions? We'll start with a very simple primitive, independence testing. You have two random variables, X and Y. You want to know whether they're independent or not, right? And conditional independence testing, where you have three random variables, X, Y, Z. You want to know X is independent Y given Z or not. These problems occur all over the space, right? And a very basic primitive in many, many, many applications. Okay, so before we go into conditional independence testing, I want to take, because many of these can be thought of as estimating divergences or distances between distributions. We start with a very simple primitive. You have two distributions, P and Q, and you want to estimate whether P is equal to Q or not. Of course, somebody gave you P and Q, you can just look at it and say, but you will not be given P and Q, you will only be given sample access to P and Q. Okay? So you get n samples, and the main question is, can we estimate, whether they're the same or not, or more generally, can we estimate the total variation distance? It's one particular distance metric between any two distributions. Okay, so when the data X is in low dimensions, for example, you first estimate P, then estimate Q, then you compare, right? But when you go to very high dimensions, all the machinery breaks down. So lots of work in information theory, theoretical computer science, statistics on estimating, total variation distance. There is sample complexity results, which usually look like when n is the alphabet size. Let's say X takes values in a discrete alphabet of size n. Then your sample complexity is order n to the 2 over 3, depends on the settings, n to the 1/2. Okay, so first, not much is known in the real valued case, but even more importantly, when you go to high dimensional data. What do I mean by high dimension? The X itself is a vector, x1 up to xd, right? So now it's d dimension. Even if it's on the binary alphabet, each of the coordinates, like a gene, right, is a d-dimensional vector. Now, even though each of them is binary, the vector is in dimension 2 to the d. So n will look like 2 to the d, and it makes it very difficult to apply any of this existing knowledge. Okay, so the curse of dimensionality is kicking in. But wait a minute, if you cannot distinguish between P and Q, how are you able to distinguish between samples labeled 0 and samples labeled 1 in a classifier? It's exactly the same problem, right? You have samples labeled 0, samples labeled 1. How did the classifier learn whether it's a cat or a dog when X is in very high dimensional space? So essentially, these classifiers exploit some generic inductive bias. Okay, so let's keep it at that level. So now, can you use classifiers to do total variation distance estimation? So what would you do? You have samples from P and some other number of samples from Q. You may not have exactly n samples. You may have np and nq. Doesn't matter. You label them 0 and 1, send it to some black box classifier, and get the Bayes error, or let's say the optimal classification error. There's a nice relationship between the optimal classification error and the total variation distance. If you knew the classification error, you can predict the total variation distance. Of course, you don't know the optimal classifier's error. You only know your classifier's error. But if your classifier is powerful enough, or you believe your parametric family is powerful enough, then you have an approximation of this. Okay, so if you want to do distance estimation, the total variation distance, just run a powerful classifier, and you can get some approximation. In particular, you can get a lower bound on the divergence. Okay, so let's go to independence testing. Can we do independence testing using this primitive? So in independence testing, you have samples of the form x comma y, right? X comma y, and xi, yi, are the samples. And you want to test whether x and y are independent or not. Does x contain information about y or not? And that's the data. And now you want to solve this problem. Let's say you want to estimate the total variation distance between P and PCI. PCI is P conditionally independent. In this case, it's just independent. Okay, so what you can do is you can try to build a classifier which tries to distinguish between the data which comes from the independent distribution and the data which comes from the natural distribution. But wait a minute, nobody gave you data from the independent distribution, right? You just have samples from the joint distribution. What are you going to do? One obvious thing you can do is essentially so you have your data table with x and y, and for each xi there is a certain yi. But you want x and y to be decoupled, so you create a data where y is just permuted. For each xi, you pick up a random yi from your observed y's. So we call this the permutation data. And a permutation data can be shown to emulate the independent distribution. So now you have samples from both, and you can actually test. Okay, one point which I'm not going into detail here is one very useful consequence of using this methodology, especially in many scientific applications. You want to get strong p-value control. So p-value says what is the probability that even though it is independent, you're declaring it non-independent, right? So you want to get a control on this number. So I'm not getting into the details here, but if you use this methodology, you can get strong p-value control, irrespective of what classifier you use. So you can bound the probability that you wrongly declared something to be independent. not independent, right? Wrongly declared something to be not independent. Okay, so I'll just not go into that. So the methodology is basically that you split the data equally, and then you have the natural distribution, then you have the permuted distribution, and then you run a classifier. You get a classification error, and you can use that to basically get an estimate of the total variation distance. Any questions? Okay, so independence testing was not actually our work. This is prior work from David Lopez Paz, basically saying that you can use standard classifiers to actually get independence testing. Okay, let's go to the area of conditional independence testing. So conditional independence testing is a very important primitive in all kinds of problems. For example, in graphical model testing, if you want to know if a variable xi is related to a variable xj, you're testing whether xi independent xj given everything else. So what that means is z is usually very high dimensional. You're doing a conditional independence test where z is in very high dimensions. Okay, let's just remember that fact. Now you have two data sets. One is coming from the, you don't have two data sets, but you have two hypotheses, the conditionally independent hypothesis and the not conditionally independent hypotheses. And now the problem is you're not given data according to the conditionally independent hypothesis. So an important question is how can you actually generate data from the conditionally independent hypothesis even though you have only data according to P? Okay, so one way to think about it is to say that, so given Z, right, what it means is instead of saying I'll permute the Y's randomly, you can say for a given Z, I'll find some neighboring Z's and permute the Y randomly among them, right? So because it's a given Z, you see for a given, so you take an X and take that Z and look at if there is some nearby Z and you use the Y from that Z. So this is a method using nearest neighbors. And the main question here is how do you get samples according to the conditionally independent distribution? You can use Kannan or K nearest neighbor methods where you look at nearest neighbors or some kernel methods to get the conditionally independent distribution. In fact, this was proposed in Rajat's earlier work in last year's NIPS, basically analyzing this with the K nearest neighbor for the Z. So one issue we came up with is in all our real data sets, Z is in very high dimensions. If Z is in very high dimensions, and you're pushing all your work to the K nearest neighbor to find a neighboring Z, in high dimensions, you will not find a good neighbor, right? Not about computational complexity. Statistically, there are no good neighbors because Z is in 2 to the D alphabet size, and a nearest neighbor needs to be also, unless you have 2 to the D samples, you will not find good nearest neighbors. So this is a severe issue. So it's only limited to low dimensional Z, severely restricting the applicability of this method. So our approach is to basically say, if the deep learning helped overcome the classification problem, maybe the deep learning should also help us overcome the dimensionality problem of Z, right? So that was our approach. Okay, so how do we do this? So if you look at P and PCI, let's stare at, so if you look at P, P is Px, Pxz, Py given xz, whereas PCI is Pxz, Py given z. The only difference between the P and PCI is here the Y is depending on both X and Z, whereas here the Y only depends on Z. If we have an emulator that can synthesize samples from Py given Z, we can create samples from PCI, the conditionally independent distribution. So how do you get a conditional sampler? So what we want is some box which will emulate a Y given Z. We want to get an estimate of Qy given Z really close to the Py given Z. Is there any questions on this? Okay. So the main question is, how do we do this? So we saw earlier that generative models are very powerful, and the generative models can synthesize samples according to a given distribution. For example, from the manifold of faces. There is also conditional generative models, which generate samples according to the given conditional distribution. For example, you want to synthesize a person's face who's bald. Right? The generative adversarial networks can actually do very well on these conditional synthesization problems. So one approach is to say I'm going to plug and play a conditional generative model for estimating the QY given Z. And now that I have an implicit sampler, I can generate samples according to QY given Z, and that will generate my conditionally independent samples, which I will go and run my classifier on. Okay, so this will work very well if your QY given Z is close to PY given Z. Right? Somehow if you got a sampler which does very well. However, there are many known issues with generative models, and there's no guarantee that your QY given Z is going to be very good. So what we want to do is to say, even if you didn't get such a good estimate of QY given Z, we can still solve this problem. So that's the major algorithmic hurdle that we want to overcome, because otherwise you just use a GAN, conditional GAN, a conditional generative model which generates samples according to a given QY given Z, learned from the samples, and you can solve this problem. So our main result is a novel bias cancellation method which works even if QY given Z is not accurate. What do I mean by not accurate? It only needs to have some non-zero property. If the PYZ is non-zero, QY given Z should be non-zero. It's a very low bar on what the criteria is. So let me explain this bias cancellation methodology. Okay, so we call this paradigm. So this is not just one particular algorithm, but a paradigm for doing conditional independence testing. We call mimic and classify. So mimic is a module that generates samples according to the QY given Z, and classify is a paradigm where you use the classifier. And embedded in our methodology is a bias cancellation method. So let me explain this paradigm. I think this is the most important slide. So you have the data generated according to P, X, Y, Z, and we split the data into two parts. One for the regular P, and the other hoping to get samples from P conditionally independent. We want to generate samples from the conditionally independent distribution. Okay, so what do? Is we take data set, to get the next part is to mimic the QY given Z. So we have a mimic function which could be a generative model which takes the Z and spits out a Y, the Y according to some distribution QY given Z, learned from samples. Okay, so you get this sample Yi prime, and now you embed it back into the data, you get Xi, Yi prime, Zi. This is the new data. And if, for example, Q was equal to P, then this is indeed the conditionally independent distribution. Okay, so we have this. And what we can do is, using our paradigm of using classifiers for distance estimation, we have samples from both of these, send it in to a classifier, and you get some classification error. Right? So we call this classification error EXYZ. And the only thing you can prove, and one can convince yourself that even if Q has some error, then this no longer reflects the true distance between P and PCI. Okay, so what can we do? So here is an idea. So the mimic function, if you remember, is only playing with the YZ relationship, right? So our idea was to cancel the bias. So if you look at this, there are two reasons why you may be able to classify well. One is because PY given XZ is very different from PY given Z. That is one reason you can classify well. Another reason is maybe PY given XZ is another reason is PY given Z is very different from QY given Z. That may also be a reason why you get a good classification error. Right? Okay, so how do we surpass that? Very simple idea, very powerful. Drop X from the samples. Now you have a bunch of samples having only Y and Z, right? Now, essentially, the test that you're doing is distinguishing between PYZ and PZ QY given Z. That's the new test that you're doing. So this classification error gives you EYZ. So 2 errors, 2 classification errors, 2 classification problems, 2 errors. You get EXYZ according to this classification problem, and EYZ according to this other dropped classification problem. This is essentially the bias in this term. Okay, so here is a very clean algorithm. You take these 2 errors. If the 2 errors are the same, you say that really the X is not playing any role. So it is conditionally independent. But if the 2 errors are very different, you say that, yes, there is a error. There is a difference. The data is not conditionally independent. So the main result is, as long as the density function satisfies just some absolute continuity properties, the main result is the expected value of the error that you get from the first one and the expected value of the error you get from the second classifier is 0 if and only if the null hypothesis is true, which means the data is conditionally independent. This is the main result. So wait a minute, what happened here? What happened here is we, instead of outsourcing a lot of work to the mimic function and putting a lot of pressure on the mimic function to output a good py given z, we are saying classifiers are very good, and we are more sure about classifiers than we are about generative models. And Sewoong will show some issues with current generative models. So we are saying we'll outsource all the work to the classifier, and the classifier here is trying to extract signal from y and z. Here it's trying to extract signal from x, y, and z. And by looking at the differential, we can actually solve this issue. So this is the main question. Oh, not timeout.
So do you use the same samples for 2 tests? Or
No, you use different samples. Yes, thank you. Yes.
How can you guarantee that property Q is something synthetic?
Yes, yes.
So how can you guarantee this?
Okay, very good question. Thank you. So since our property is not too heavy, it's only saying that you need to have non-trivial mass on almost all the points. So we have many ideas. For example, one idea would be that you would take a mixture of a generated distribution and some uniform distribution on y. If you put a uniform distribution on y, then this property will always be guaranteed. So there is also some finite sample results where we say that, of course, the closer you are to qy given z to py given z, the stronger the signal that you're operating in. This is a 0 non-zero result, whereas we also want stronger signal in case of conditional dependence. And the better your py given z, qy given z and py given z are closer, the stronger signal you will get. So in some sense, only the 0 non-zero issue is outsourced purely to the classifier. The finite sample issue, some hard work needs to be done in the mimic function. Okay, so I think I can bypass all the theory. So one interesting thing is we have to use some coupling characterization to actually solve this. Going to what mimic functions we use GANs, which Sewoong will talk about in great detail, which generates samples according to some conditional distribution if you train it. We also can use regression. If you regress y on z, some nonlinear regressor, to get y on z, then you can say that you generate samples according to some variational type thing where y hat is generated according to some noisy version of the regression estimate. So you can try various things, and here is a simple example where if your z grows in dimension, so you just stare at, this is the area under the ROC curve, and the x-axis is the dimension of z. As the z dimension grows, the GAN combined with our bias cancelling methodology actually has a kind of significant gain. We're running more experiments. This is fairly recent results, so it'll be on archive in the next week. Okay, so it also can show some performance improvements on real data sets. I think I'm way out of time on this part, so I'll stop with this, but just mention that this is not restricted to purely property testing. You can do information estimation, conditional information estimation, open problems. Let me maybe go directly to the open problems. So there is work from others, for example, from Alex Demakis' group, trying to say that you don't need really compressed sensing if you can understand the manifold of the data empirically you can use generative models to actually get better than compressed sensing. So again, I'm out of time to cover these things. But there's a bunch of open problems. For example, in statistical property testing, how far can we push this? Can we do conditional independence, conditional mutual information estimation? For example, right, this conditional mutual information plays a vital role in the recent debate on bias in machine learning. For example, you may want to say that salary should not depend on some personal variables given some performance, and you want to control this. Can we actually get estimates of, but in reality, all of these data are going to be high dimensional. How do you get control on these variables? So I also mentioned briefly information bottleneck and deep learning, and there is a hotly disputed relationship between them, and part of it is problem in information estimation. So our community should participate more actively in this debate. And finally, we are relying on GAN-type methodologies for generating samples. It does not work well in very small sample regimes. What can we do to bridge the gap? So I'll stop my part and let, any questions on this part before we move on? Okay, thank you.
Right, so we're gonna move to the next part where the part 2 is 2 parts, A and B. We're gonna talk about how we can use some of the knowledge from theory and information theory to understand and say something about deep learning. And in part A, I'm gonna talk about generative adversarial networks. All right. Oh, so that's where we are currently on time. Right, so neural network can be used to train generative models. And the question is, how do we train a generative model that can model distributions that lie in very high dimensions with very complex samples. For example, you might want to model the distribution of faces, which in this case is 1,000 by 1,000 dimensions in 3 colors, so it's 3 million dimensions. And I think Sreeram kind of gave away my punchline by showing this earlier, but there are 5 images, and 4 of them are generated by a GAN, and 1 is a real person. So if anyone brave enough would venture out and tell me which one image is the real person, anybody? The most left one? That's a GAN image. Okay, let's count how many, should take less than 5 trials. Any other guess? Yeah, it's the middle one is a real person. Thank you, you're very perceptive. Right, so GANs are pretty good. But the problem, if you're gonna use traditional methods, is that if you're gonna use parametric models like mixture of Gaussians to model this, you're gonna fail because it's so complex. If you use Gaussians, it's gonna completely wash out. And if you wanna use non-parametric models like kernel density estimators or nearest neighbor methods, then the dependency dimensions is typically exponentially bad, so you won't get anything. So what we want to do is we're going to train neural network generative models to learn the distribution. And neural network generators are, as I said, something like this, which maps a smaller dimensional noise in a Gaussian, typically, distribution to whatever dimension you want to produce, can be trained to produce examples like this. And the breakthrough happened when Ian Goodfellow came up with adversarial training for training these generative models. And the idea is that it's going to work on 2 separate neural networks, one for the generator that I showed you before, and there'll be another neural network that performs discrimination. So what generator tries to do is map noise into examples so that it looks realistic. What the discriminator is going to do is it's going to take in each of these examples that are generated and real and try to tell which one's real and fake. And the analogy people like to use is that the generator is playing the role of a forger trying to make fake money, and the discriminator is being a detective trying to detect which one's real and fake, and you let them play against each other long enough, they'll get better and better. Eventually, the generator can fool any discriminator. So that's the idea. And one thing, in this training, you need to choose a particular loss and train it on minimax loss so that the discriminator tries to maximize, tell them apart, and the generator tries to minimize to make it hard to discriminate. And you alternatively update the weights of these two neural networks, fixing one, using gradient descent on the other. And typical choices of loss is, again, this is exactly binary classification for the discriminator. So cross entropy loss is typically used, originally proposed. And if you look at what it means for the GAN training, is that you can write down the cross entropy loss, assuming you have infinite samples for now, and assuming the class of the discriminator has representation power to represent any function, then you can compute the gradient, set it to 0, and the optimal discriminator function is just going to be outputting the probability that the example that you have came from the real distribution normalized. And you plug that back into the original loss function, then what it means for the generator is that you're actually minimizing what's called the Jensen-Shannon divergence, which is kind of a symmetrized version of KL divergence. So what you're asking the generator to do is get close to the real data in Jensen-Shannon divergence. But for the theoretical analysis that I'm going to do in this tutorial, we're going to use 0-1 loss, which means that you're going to minimize this loss, similar, without the log. And the discriminator is now constrained to output either 0 or 1. You can do the same analysis and say, get the optimized discriminator is going to be just indicator whether it's more likely to have come from the real data or fake data. Plug that back into the loss, and what pops out is the total variation distance between real data and the generator distribution of the current, in the process of training, the current step of the generative model that you have trained so far. So you're asking it to get close to the real data in total variation distance. And there are other popular choices that I won't go into in this talk. Any questions so far? Okay. Right, and one of the major challenge in training a GAN like this is called mode collapse, and that's going to be the main focus of this talk tutorial. And what it means is that collectively, mode collapse means a lack of diversity in the trained and generated samples. For example, if you have a mixture of Gaussian in 2 dimensions, just to make it easy to show, 25 mixtures, 5 by 5 grid, you train a GAN, off-the-shelf GAN on this data, take the, I don't know, 10,000 or 1,000 samples, it's going to look like this, the generated samples, meaning you missed many of the modes. On average, the off-the-shelf GAN that are popular is going to capture about 17 out of 25 modes. So diversity has been lost. Some of the modes has been collapsed. Another example people like to use is called stacked MNIST, where the real data is generated from the famous MNIST handwritten digits, where you take a MNIST digit, color it green, put another one in blue, another one in red, so you have 3 digits put together, so each one is a real sample, looks like this. And you train, again, the off-the-shelf GAN tailored for images, which is called DC GAN using convolutional neural networks. There are 1,000 modes, because each color channel has 10 modes, it's product, so 1,000. Typical one gets about 100 modes. Not only that, you can see that the images are not sharp at all, and there you see a lot of repetitions. So these are mode collapses, and there are ways to improve upon it if this is a task you want, but then there might be other tasks you want, like, for example, conditional GAN, where you condition on whatever label you have, maybe person or a horse or a truck, and you want to generate many samples using GAN. And the first architecture that we're able to do it will show a lot of repetitions. These are independent, conditionally generated samples from the GAN that was originally very popular, and you can see them, they're more or less the same. And there are ways to make it better, and then there'll be another task, for example, like you have a text, a sentence, and you want to generate images. If you generate one, it looks pretty okay, but you get the repetition. So mode collapse is a fundamental part of the GAN. And what we want to do is come up with a way of bringing a theoretical lens, particular detection theory and hypothesis testing, lens on it so that we understand what's happening so that it can lead us to come up with a better architecture and loss design that's gonna eliminate or try to eliminate mode collapse. So that's the name of the game. So we start with our definition of mode collapse, because so far mode collapse was hand wavy. So this is a theoretical formal definition that we propose, which is, I'm gonna say, given a pair of distribution, P is the target distribution, real distribution, Q is current generator distribution. Given these two, I'm gonna say that in this probability space, this pair exhibits epsilon delta mode collapse if in the domain of the samples, there is a subset S where there's something larger than delta in the original real distribution, which was collapsed to be less than something small, less than epsilon. Okay, if that happens, for any given P and Q, I can tell you whether it has particular epsilon delta mode collapse or not. And this leads us to understand or look at pair of distributions using two-dimensional region, which we call mode collapse region, we'll go into in a bit. And that has many, many benefits for us. It's gonna tell us how to understand mode collapse. And it's gonna give us intuition on how to fight mode collapse, come up with a better architecture. And most interestingly, it's gonna give us a new proof technique where we can actually prove that our architecture provably penalizes mode collapse. So that's the whole plan. Let's start from the beginning. Question?
Could the definition tell the mode collapse and the merely fail of the training?
Right. So this talk is going to purely focus on mode collapse. Failing of training itself, there is no theoretical way of understanding it currently, but in empirical simulations, they go together. If you eliminate mode collapse, almost always you get better samples, and I'll show you some of them.
So the definition itself contains the mere mistakes, mere failure.
So it only tells you how much more. Okay, it's a definition. It's a name I'm giving. You give me P and Q, and I'll tell you whether it has epsilon delta mode collapse or not. And main reason is that now we can compare if you have Q1 and Q2, which one has more mode collapse. We can talk about it formally, mathematically. Okay. Let's wait a little bit and see how it plays out. So here, epsilon and delta, think about it as some abstract thing where if you have large delta and small epsilon, it's more mode collapse. So if you have some epsilon delta and another epsilon delta, sometimes they can be compared, sometimes they cannot be. But for what you need to look at it is the region, and maybe it will be clear. So you don't fix epsilon delta. The way you look at it is the whole achievable region of epsilon delta for given P and Q. For example, let's say this is a toy example that I'm going to use almost all throughout. Let's say P is a uniform, only because it's easy for me to draw. And let's say your generator is Q1, which has mode collapse completely here in some region, and is okay in other regions. This is my target distribution and generator distribution. Then given two distributions, from my definition, I can represent it as a two-dimensional region, which is a convex hull of all achievable epsilon and delta points for this P and Q. And how you get this region is that, well, you try to find S that's most mode collapsing. Here, epsilon is 0, delta is 1. So you know delta is 0.1, so it's 0 and 0.1 is achievable for this P and Q. And you grow the set, 0 and 0.2 is achievable. And in this way, because we only care about delta bigger than epsilon, the lower bound is always 45-degree line. And it's a convex set by definition. So you only need the upper bound, and this is how you get it. And you traverse it in this way from most mode collapsing to the least, and you get the whole upper region, and you get the whole region. And what's nice about this region is that it's going to tell us a lot, almost everything we need to know about this distribution. Given this, I can throw this away and do everything on this. For example, let's look at two distribution. The P is the usual thing. Q1 is mode collapsing because it completely lost some region. And Q2 is less mode collapsing. It's balanced. But these numbers are chosen such that the loss we see when training GAN, the total variation is the same. Meaning, GAN cannot distinguish these two, although it's obvious that that has strong mode collapse and this one is weak in a hand-wavy sense. And how do we make it formal is you look at the corresponding mode collapse regions, and one is much bigger than the other. Bigger region means more mode collapse. So if you have such a dominance in the region bigger than this one, then you can definitely say that one has more mode collapse. That's one reason we came up with the definition. But you can read a lot more. For example, you can read any divergences from just the region. And for the purpose of this talk, I only need to read off total variation, which is a very simple geometric property of the region, which is you take a 45-degree line and find where it's tangent to the region, and how much you have to shift it is exactly the total variation distance. And it's the same for this too, because that's how we constructed these distributions. Right. Another interesting way of looking at it is what is GAN doing then? So let's think about GAN training from the beginning. You have a target distribution, you get samples. So originally, the generator is randomly initialized. So the distribution it outputs is completely random, has nothing to do with that. And your region will be large, and your total variation might as well be 1. And in training GAN, what happens is that you're pushing a 45-degree line down so that the region you want it to get smaller. Smaller region is just better. If the region is completely crushed, it means two distributions is identical. So the region gets smaller, and you're through gradient descent, your distribution gets closer and closer over the iterations of your GAN training until it converges and doesn't move anymore. So in some sense, that's how I view what happens when you're training GAN. And what it resembles is that now it kind of tells you why mode collapse is happening, because at this point, you would want something to be like this, where there's less mode collapse, but there's no differentiating from the GAN training itself, because the only thing you look at is the loss as seen through the discriminator, and they look the same. So the big question that we have is, how do we differentiate these different generators that have maybe look the same from the loss that you gave me, but have vastly different mode collapse? And how we do it, I'm just gonna jump to the punchline and give you the intuition later, is what we call lifting the loss to the product distributions. And what I mean by that is that, well, instead of looking at total variation between P and Q, look at the total variation in the lifted space as in the product of this P, M of them, and product of Q in the M's, or the lifted space, and that one is going to naturally penalize mode collapse. I'll tell you why. But this intuition is related to the long historical knowledge from detection theory and hypothesis testing dating back to Blackwell's results from '53 and comparing stochastic experiments, which can be translated to reverse data processing inequalities related to this mode collapse regions, and my work in differential privacy with Peter Kairos and Pramod Vishwanath. But what we really need to know is, how does it work? There are many ways to implement this idea as architecture, but I'm gonna give you the simplest. So one of the reviewers called it embarrassingly simple architecture. That's gonna implement our idea. And the reason is that I just wanna isolate out how our idea improves the performance and nothing else. Because if I do something complicated, there'll be other factors kicking in. It'll be hard to disentangle them. So what I'm gonna do is what we propose is called pack GAN. So you give me your favorite GAN, which is represented by your generator architecture choice, you choose it, your discriminator that you choose, and the loss that you're gonna choose to optimize. Doesn't have to be 0, 1, anything is fine. And you also give me all the hyperparameters you use in your training. And I'm gonna make a very small change in the discriminator where the input layer, I'm gonna increase it by a factor of 2 if I'm gonna pack 2 samples together, or M if I'm packing M samples together. And then train in the usual way. So what happens is that now in the training, I'm gonna draw M IID samples from real or from fake. So essentially, this is sync samples from the product distribution. And that's the only change I'm going to make. And let's see how it does. So on the benchmark data set on the mixture of Gaussians, if you take the same GAN, even the code, and make this small change, then with packing, pack and 2 means you pack 2 things from the mother architecture, which is GAN, you get about 24, and with 3, you get a little bit better, 4, a little bit better. And more interesting is the stacked N list. So these are the results that we didn't run. This is just taken off exactly from this paper that they run. And what we do is we take the code of DC GAN and pack it so that we can pack DC GAN 2, 3, 4, and keep all the hyperparameters exactly the same. So one thing is nice is that typical in deep learning, a lot of time goes into hyperparameter tuning because you have to show that your new architecture works well. For us, it saves a lot of time because we don't do any hyperparameter tuning. And with PackGAN2, you already get all the 1,000 nodes. And there are many such examples in our paper that I'm not going to go into more. But OK, now that's the empirical evidence. So it's clear that something is happening, something fundamental to training GANs. So let's try to understand what's happening. So my intuition for coming up with this architecture was the following, that we can, in some sense, measure or differentiate how much mode collapse is present in different generators, generative models, using lifting. And the idea comes from the reverse data processing inequality. In this context, what it means is that, well, look at 2 distributions and corresponding regions. If there is a region dominance, one is bigger than the other, then the dominance will be preserved if you lift it. Seems very trivial, but actually proving it is quite non-trivial. But the intuition is that, well, if you look at the region, and then let's say you lift it to the second order space, okay? And there'll be some different regions. The region is going to evolve. And if you look at how it evolves, how it grows, it's going to grow much faster if you have a bigger region than the slow region, meaning whatever is kind of remainder here is going to contribute to how fast it grows. And although they look the same from total variation now, if you lift it, they're going to be different. And something exciting happens. If you had a mode collapsing one, the total variation is going to shoot up, whereas the non-mode collapsing one, it doesn't change too much. And you can do it for any lifting of M for this particular toy examples, and see that this trend continues, and then the mode collapsing one will have fast increasing loss or total variation over how many you pack, then compared to the non-mode collapsing one. So when you have a GAN trained on this lifted space, it will naturally learn to penalize more the one that has strong mode collapse. So that's the intuition. But this was just on 2 toy examples. And what we want to do is bring an analytical lens to prove this for any distributions in any high dimension and any complex domain. And here is our proof idea. So what we're going to do first, our strategy first is I'm going to look at all the distributions P and Q in any dimension in any space, and look at all of this P and Q that have the same total variation when it's not packed. So subject to total variation being equal to some tau, let's say. That's my feasible set of P and Q. And I want to understand how the total variation or the loss evolves, how fast or slow it evolves, by solving the following optimization problem: maximize or minimize the total variation after mth order lifting. And I can solve it. And for this particular choice of tau and m, it looks like this gray region. M, that's a good question. In practice, there's a diminishing gain. So 2 is good. Sorry? Right. What's the downside of why don't you use M50? The reason is that the dimension is increasing pretty fast. It was 3 million dimension to begin with, now 6 million and 9 million. There are other factors kicking in that's not captured by theory, which is the finite sample and large dimension effect. So in practice, we don't propose you do it for large M, and that should be solved by architectural innovations where you use different ideas, which is exactly what we're working on right now. But for this, so far, it's a proof of concept architecture. For high dimension real data, there are other ideas that we're going to use to deal with those. Thank you for the great question. Okay, given this, what we can show is that now what I want to say is that, well, among those, all the P and Q that occupy all this region, I'm just going to look at the feasible set, those that have some strong mode collapse, as I define, let's say, those with epsilon naught, delta naught mode collapse for some particular value of epsilon and delta naught, and solve this problem. And what I get, and I can solve it exactly and tell you, for the particular value of epsilon naught, delta naught, and tau, it'll be like this. In general, the trend is like this. The ones that have strong mode collapse will occupy the top region of this evolution, increasing the loss very fast. And I can solve the same thing with those that don't have particular mode collapse, and the trend will be like this, where they occupy the bottom region. So putting them together, and then I can get the exact numbers of these regions for any epsilon naught, delta naught, and tau you give me, which is in the paper. And putting them together, it looks a little bit weird. What it means is that, okay, the idea of packing, what it does is that now if you have a GAN, I'm going to do packing, and what it does is it puts a lens in front of your discriminator so that now your GAN is able to differentiate which have strong mode collapse and which have weak mode collapse. And without explicitly telling it to penalize mode collapse, it will learn to naturally penalize those generators that have strong mode collapse. Okay. And one of my personal favorite part of this work is the proof technique that goes into finding the solution of these optimizations, which heavily relies on our definition of mode collapse region and corresponding data processing inequalities. I don't have time to go over it today, but anyone who's interested, please take a look at it on the archive paper. And one remaining challenge in this context is that like a punchline of what we did is that in training GAN, there's been a lot of work in proposing use this loss with this loss and a lot of different losses. But typically, how they're compared is through experiments on real data. And they measure some scores, like inception scores. But we give a formal way, mathematical way of comparing two different choices of loss functions as far as mode collapse is concerned. So if you're considering mode collapse, then what we formally prove is that total variation distance is worse than total variation distance of the lifted distribution. Formally, we're doing that. But there's nothing that's stopping our mathematical framework to be applied to other things, other losses. For example, using exactly the same framework, I can show that total variation is also worse than Jensen-Shannon divergence by solving this optimization and looking at how the distribution that has same total variation expand in terms of Jensen-Shannon, it penalized mode collapse. If I change it, it'll be blue one on the top and red on the bottom. So what we can do is we can put on ordering, sometimes, not always, because sometimes it can happen that red and blue completely overlap for some distributions. That's also a possibility. They're incomparable. But when they are comparable, we can compare it. Just as solving this optimization can be quite hard for some other things you want to do. Maybe you want a Jensen-Shannon here and F divergence here. Gets trickier. But I think our community is expert on those things. This has nothing to do with actual GAN, or it's a mathematical question, which we are really good at. So those are the remaining challenges. Put different losses there. Tell us which one is better than the other and put them in an ordering. Okay, so that's the mode collapse part, but there are other very interesting parts in theoretical understanding of GANs. I'll just mention a few because I'm running out of time. So one is generalization of GANs. If you train a GAN under certain conditions, can you guarantee that the solution you get out of a GAN, how close it is to the real data, and give a guarantee? Some efforts has been made, which are the first steps, and very interesting trade-offs come up. But I think I'm running out of time, and I'll have to skip this part. Please take a look at the references and my slides later, or talk to me if you're more interested. And there's another work by David Che recently trying to understand the role of discriminator in terms of simplified models where you have a Gaussian distribution you want to emulate, and you use a generator that generates Gaussian distributions and tries to understand the role of the discriminator. And the message there is that you need to use the discriminator of the right complexity, which gives you fast convergence rate. If you don't use the right one, you can pay in the convergence rate, which is very exciting result. And finally, there has been interesting work trying to use mutual information to give interpretability to GANs. So if you just train a GAN right now, the Z1 and Z2s that you learn have no meaning because they're rotationally invariant. But ideally, what you want is that maybe you want Z1 to represent what digit you are outputting, Z2 to represent what rotation they are in, and Z3 to represent how wide they are. And this can be done by incorporating mutual information between the latent space Z and then the output image X. And there's some exciting work in disentangling the interpretability of the latent dimensions. So with that, I think I should thank the amazing collaborators that I work with in this project, and I can take any questions, if there are any. Well, Sreeram said so. It's a question. Right, so a lot of gain comes from lifting to 2 seconds, and then there are diminishing gain. And empirically, we can show you how much gain we have. So far, there's no analytically saying how it depends on M exactly. What we can say is that all of them give you gain in terms of mode collapse, but that's what we know currently.
All right, so we are currently in Part 2, Information Theory for Deep Learning, and Sewoong covered some aspects of generative models. Now we're going to look at a problem in supervised learning where information theoretical lens actually comes in useful. Okay, so this is joint work with Ashok Varadan, who is a grad student at UIUC, Sewoong, Pramod, and myself. Okay, so what is the motivation for this particular part? As you can see, there is a word here, gated neural networks. So first I'll explain where gated neural networks have made a big impact. So there are two families of neural networks, recurrent neural networks, called LSTM, long short-term memory, and gated recurrent units, which have done very well and are typically state-of-the-art in many, many speech recognition and time series type tasks. And here just an example of Google Duplex. Some of you may have seen the videos where there is an automatic conversation agent which can make reservations for you. And these use things like LSTM and GRU. And not only that, very popular in many applications. Okay, so what is this gated neural networks? So feed-forward neural networks we've seen till now. Right? So it's just feed-forward neural networks. There's input, there's a hidden layer, there's an output. Recurrent neural networks also made a showing in the part on communication. So the recurrent neural network maintains a state that gets recursively updated. And due to several problems in training this and representational issues, typically people use gated recurrent units. And a gated recurrent unit is exactly the same as a recurrent unit, where the state is getting updated, but you have an option to not update your state. Hey, I don't want to update my state right now. So it's an option to not update your state. right? It's an option to not look at the input. There are various levels of gating. But the gates essentially decide, whether you are going to pay attention to the new input or to the old state or not. Okay, so what is this gating phenomenon? If you just extract out the gating out of the recurrent neural network, it's a very simple phenomenon. So here's the simplest possible example, simplest non-trivial example. So you have an input x, okay? And let's say you want to run some regression. You want to make some prediction from x. One way to do it is to say that x gets multiplied by takes an inner product with a, and then there's a nonlinearity. So it's a simple regression function. A neural network, a two-node neural network, would do this and this, right? Same x goes to a1 and a2, and you calculate this. And then in the last layer, you just take some linear combination of the two. This is a standard neural network. However, in a gated neural network, there is a function f which decides how much you pay attention to this and how much you pay attention to this. This parameter f is not fixed a priori, but varies based on the current input. So to think about it another way, you can think of this f as deciding which expert to rely on. There are two experts, two hidden nodes, two experts. And which expert to rely on, you should not always rely on one expert versus the other expert. You should look at the input and say, hey, in this regime, Sewoong is better, or in that regime, Pramod is better. Right? So you always look at the regime and then decide what to do. So that's what the mixture of experts does. Basically gating based on a certain function and the input, which node to look at, which expert to look at. Any questions? The basic model is going to be used again and again. Okay. So, like I said, mixture of experts generalizes two-layer neural networks in this way. Because in a two-layer neural network, just two nodes, then the two nodes gets mixed up based on just fixed coefficients, whereas in a mixture of experts, or a gated neural network, as we call it, which node you rely on depends on the current input. Okay, so mixture of experts are a smaller building block in gated recurrent neural networks. But also by themselves, they've played a role in deep neural networks as one more component. So this is a paper called Outrageously Large Neural Networks, as though other neural networks are not. But they can actually show that on many NLP tasks, throwing in a mixture of expert layer in the middle can actually improve performance significantly. Okay, what is known about MOE? It has a long and distinguished history, 25 years. And no provable algorithms for learning parameters. Okay, so what is the question? The question is, given n IID samples with no model deficit. What do I mean by no model deficit? The data comes from exactly the same kind of a network. Right? It's kind of your best case, dream scenario. Right? You've fixed a two-layer neural network. Data also came from a two-layer neural network. Can I just figure out the parameters? Right? Very simple, grounded question. Okay? No model deficit, keeping with the theme of this tutorial. Questions? Okay, so given n samples, can we recover the parameters? This is a standard parameter recovery question in statistics. And what would you do normally is, yes, question? F and G are fixed functions, like they're called activation functions in neural networks. You are not optimizing over F and G. Great, thank you. F and G are known, only W, A1, A2 are open. Okay. Any other questions, clarifying? Okay, what can you do? We don't have parameter recovery. I'll cover that and what we know and what we generalize. Thank you. Indeed, so even in regular feed-forward neural networks, the problem is hard. I'll highlight why, and there have been some approaches to break the difficulty. So what you would do is you take the loss, right? You have y and you have a prediction, psi of x. Theta is whatever is your general parameters, and then you do some gradient descent. Right? If the loss is convex, then the problem is easy. However, the loss is highly non-convex. Why would it be? So let's understand this in the context of a two-node neural network. So you have inputs, you have two nodes, and then you have an output. And let's say the parameter, the vector connecting the input to this hidden node is A1, and this node is A2, and linear coefficients W and W2, and then you get the output. Right? So very simple neural network. So the loss function now depends on A1, A2, W1, W2. That's what we're optimizing over. Okay, first, observe that there is a permutation invariance. If you swap the two nodes, nothing happens, right? Which means the loss of A1, A2, W1, W2 is the same as A2, A1, W2, W1. Like you put A1 here, A2 here, the functions are the same, so there is no difference. Well, once you have this permutation invariance, it brings up a big monster, because if the function were convex, if the loss function were convex, then any convex combination of these things should work, should have a lower loss, and this is the optimal one, therefore it should have the same loss. And what that would mean is choosing both the A1 to be equal to A2 is optimal. And that doesn't make any sense. Right? So the permutation invariance inbuilt in a neural network automatically creates non-convexity for you. Because you cannot be convex, and if you had convex, you only could do trivial things. You could not do non-trivial things. Questions? Okay, this is not specific to MOE, it's true for general neural networks. Okay, so gradient descent may not work. So like I said, the MOE has an additional layer of complexity, the classifier sitting on top of the regressors. So we have to deal with both. Already it's non-convex, and it's more non-convex. What do you do? Okay. Okay. So can we have a certain modular structure? So normally in a mixture of expert, or in any scenario where there are multiple latent variables, an expectation maximization or an alternating optimization type framework usually works. You know one, it's easier to know the other. Right? So how do we break the gridlock? Right? So you can try an EM algorithm, it gets stuck at exactly the same local minima as the gradient descent. So you can't do much more with EM type algorithms. So what do we do? So in this talk, we quickly highlight two approaches that we have, and in general, the neural network community has discovered to be useful for this kind of a problem. Method one, let's change the algorithm. Let's not do gradient descent on a loss function. Do some other thing, and maybe you can sense the parameters more accurately. Method two, change the loss function. Keep the gradient descent, change the loss function, and maybe you will recover parameters accurately. Okay, so in this talk, we are going to make an assumption, a generative assumption, that X comes from some Gaussian distribution. So this is a limitation of this approach currently. Okay, and even though in the whole talk I'm going to focus on two nodes, be assured that this holds for general K-node neural networks, K-node MOE, and also hierarchical mixtures of experts. I'm not going to go into all these models. Okay, first method, can we design algorithms better than gradient descent? Okay, so let's first look at the simplified problem. So what is our P y given X? So maybe, even before staring at this, what could be other types of algorithms, right? You have X and Y, right? What else can you do? If you look at it classically in statistics, the maximum likelihood estimator is one family of estimators. There is another family of estimators, the method of moment estimators. What do? They take the input and the output, right, Y and X, calculate some moments, expected Y times X. Maybe X times expected Y square times X, expected Y times X tensor X. Some moments between the input and the output. And maybe you can sense the echo of the parameters in these moments. Somewhere in the moments, these parameters are hiding, and if you can sense them out, that would be great. Okay, so that's going to be our framework, the method of moments, because the loss function minimization follows the likelihood optimization. Okay, so what is our P y given x? What is the relationship between y and x? Is with probability f, you have a Gaussian distribution with mean g, or with probability 1 minus f, you have a Gaussian distribution with mean g of a to x. This is the model for MOE formally. Now, let's go to the model without gating, right, and understand that model. As the question was raised, if you cannot solve the non-gating model, you're not going to solve the gated model. Okay, and turns out there is a very nice work by Anima Anandkumar's group, which has actually solved this problem. And we build on top of this to solve the gated neural network problem. Okay, what is the basic idea? The basic idea is to somehow construct some moment between the input and the output, x and y, some function of x and y, and the expected value of that if it looks, if it contains the parameters in some nice way, then we may be able to extract it out. And in particular, the nice way that we are going to focus on is that firstly, the left-hand side is also a tensor. For example, you can calculate x times yi times yj times yk. Right? This could be a third-order tensor, like a matrix, but three-dimensional. And you try to decompose this into sums of outer products. An outer product looks like this, ai times ai times ai, a2 times a2 times a2. And then you just multiply all these components and get a matrix. So simple rank 1 tensor. If this moment tensor can be expressed as a sum of supersymmetric rank 1 tensors. Why is it supersymmetric? Because it's ai times ai times ai rather than ai times bi times ci, which would also be a rank 1 tensor. If you have this property, then the ai can be recovered. So this is a nice result from tensor analysis. So the main question now that remains is, how does one construct this psi? So I'll show some details. I don't know how much we can cover, but the main thing is currently the construction of psi requires inspiration and ingenuity, and there is no general framework that you can just go and ask for and you can solve it. Okay. So I'm going to focus on the non-gated model and try to see if we can solve that model. In particular, let's look at the simplest possible model where there is not even 2 nodes, just 1 node, trivial model. So let's say you calculate expected y times x in this model. What is y? Y is g of a1 transpose x. That's it. That's y. If you have this model, expected y times x is the same as expected g of a1 transpose x times x. And let's forget the noise, doesn't matter. And how do we calculate this moment? That's where the Stein's lemma comes in useful. It says that if you want to calculate expected f of x times x, it's basically the expected value of the gradient of f. Okay, so if x is Gaussian, so it's a very nice property of Gaussian distributions. So there is also generalized Stein's lemma for non-Gaussian distributions using score functions. We'll not get into that today. Okay, so we can calculate expected y times x, and very nicely it turns out that you use the Stein's lemma, the gradient goes in, and the a1 pops out because it's gradient with respect to x. There'll be some other constant terms, but it's proportional to a1. The expected value of y times x is proportional to a1. Question? Currently, we're doing independent Gaussian. Yeah. You need this thing. It's easy to decorrelate, and if you get an x, then it's easy to decorrelate and get an ID Gaussian. Okay, this is something we can discuss offline. I would love to know the history of this lemma. Oh, I don't know. Maybe this was another thing that Stein wrote. I don't know, so I'll not comment on it. The same thing? Okay. Okay, good. So there are other history for the same theorem. Okay, so what can you do with this in the case when there are two mixture components? It very nicely separates out that expected y times x is with probability p a1 and with probability 1 minus p a2, and you can actually just get a very nice expression. So the first order moment between the input and output actually tells you a convex combination of a1 and a2, the parameters of the first layer. Okay, so if I give you a convex combination of two vectors, there is no way to extract the vectors. It's obvious. Okay. Now let's go to second order Stain's lemma, where you're not taking the correlation between the input y and the output x, but xi times xj, y times xi times xj. So the second moment, the normalized second moment, you subtract out the identity, you calculate expected y times xx transpose minus I. What you get is basically a convex combination of A1 transpose and A2 transpose. And if A1 and A2 were orthogonal, one can basically get A1 and A2 from the matrix. But if A1 and A2 were not orthogonal, the decomposition is non-unique, and you cannot recover A1 and A2. And we don't want to assume orthogonality. We don't know what the neural network needs. So when you go to the third moment, do the same thing. What are you doing? You're calculating y, expected y times xi times xj times xk. It's a d by d by d matrix, where d is the dimension of x. This matrix is basically the sum of two rank 1 tensors, a1 times a1 times a1 plus a2 times a2 times a2. This is an interesting property of tensors that greater than rank 3, this decomposition is unique. If you have supersymmetric decompositions, as long as a1 and a2 are linearly independent. You need very weak properties to get decomposition. Okay, so that basically solves our mixture of GLM, or the mixtures, or the two-layer neural network problem, because you basically got out the first layer without, just by calculating the moment tensor between y and x. How do you calculate this given samples? You just calculate the empirical moments and average it, and then you will get an estimate of this, and then run some tensor decomposition algorithm, which will spit out A1 and A2, which is the first layer parameters, right? First layer, each hidden node is connected to all the x, d dimension. So this spits out the d dimensional parameters. Questions? So this is what goes on for two-layer neural networks. Now that we can solve, so this is earlier work. Now that we can solve two-layer networks using this methodology, how do you solve gated neural networks? One may go and try to plug in the same methodology. Remember, in our problem, there is A1, A2, and W. Right? W is what determines how to switch between the experts. So now, if you go and try the same thing, it doesn't work. Why doesn't it work? You have A1 and A2, but also they interact with W. And what you get is not a supersymmetric tensor. You get A1 times A1 times A1 plus W times A1 times W, all the combinations. And there is no way. So the Kruskal's theorem doesn't hold in this case. So you cannot decompose and obtain these parameters accurately. Okay, so what do we do in this case? Our main insight was that you should not only transform the input, but also transform the output and compute some cross-moment tensors appropriately. And indeed, our main results are essentially what those moment tensors are that actually give you the right decomposition. So we call them, so it uses the theory of Hermite polynomials and other theory about score transformations. And the main result, which I won't go into the detail of why these particular cubic and quartic transformations work out, but they're general and they can handle arbitrary nonlinearities. And for each nonlinearity, we can calculate some nonlinear transformation on the output, which, if you take the moment with, will give you the right answer. So this is our main result. And as I said, this is the innovative part where you have to figure out what would work. Okay, so now using this methodology, as you can see, you can recover A1 and A2. Right? You can recover A1 and A2. What about W? Right? It turns out, if you want to recover W, so you can recover A1 and A2 using this method. You can recover W using, see, if you look at this, if you knew A1 and A2, these paths are known, and really it looks like a classification problem. Because you're trying to decide which expert played a role. However, there is a latent variable in this model, and you need EM algorithm to solve even just the classifier. And our main result here is a global convergence of the EM algorithm with arbitrary initialization. And as long as you initialize with the right A1 and A2, or approximately the right A1 and A2. So we have robustness results also. So I only talked about the consistency type results. We can also convert these into sample complexity results. How many samples do you need in order to estimate the moment tensor to a certain accuracy? And what is the error in going from the observed moment to the decomposition? You can bound all these things, and you can get sample complexity results. Okay, I cannot get into method 2, but I'll just tell you one slide on what the method 2 is. Normally, you have X, goes through the neural network, you get Y prime, the prediction, and there's some loss function between Y and Y prime. And you try to optimize this loss against the parameters. So instead of using this architecture, recently there has been an alternative proposal where you use X, Y, and theta, the parameters, in some other way other than the natural setup of the neural network. And you can combine them in some other way and design some other loss function G to actually do gradient descent on this loss, will recover the true parameters theta. So this has been done in the 2-layer neural network case. And our main result is to figure out a decomposition of how you can take X, Y, and the parameters, and you have to do some careful analysis where you use one loss to recover A1 and A2, and you have to switch the loss, and then you'll recover W. So it's a very innovative architecture in that sense. Normally, the same loss function is used to learn all the parameters. Here, for different sets of parameters, you use different loss functions. And the loss functions themselves have some tensor property, permutation invariance, which bypasses the non-convexity barriers. Okay, I'll conclude this part by presenting some open questions. So the generalization to non-Gaussian inputs is a very interesting open question. Learning algorithms directly for the time series. We started with recurrent neural networks with gating. We have not gone back because when you unroll a recurrent neural network with gating, you get a mixture of expert, not one layer, but many, many layers. It's a deep mixture of experts. And even for just deep neural networks, the same types of tensor algorithms have not been figured out. So it's a very interesting open problem that I think our community can engage in. And this can potentially have ramifications in the time series problem, and because there is more structure in that. So with that, I'll conclude the 2B part, and we're happy to take any questions among all of us.